This particular video is going to be about a set of curves known as conic sections. Here's a cone, and conic sections are formed by taking cuts into this cone in various ways. Now, the curves that are formed by taking these particular cuts or sections are very old. They were known to the ancient Greeks from about 350 BC onwards. But not only are they very old, but they also are very modern. The dish aerial that's outside your house that brings in sky television is based upon the reflective property of one of these conic sections that we're going to be having a look at. Jodrell Bank Telescope, a radar telescope that pierces deep into the universe, picking up signals, recording them for us, again is based upon a reflective property of one of these conic sections. So although they are, ancient even though they are, they have very, very important modern uses. So, let's have a look at our cone. Let's begin by describing some features about the cone itself, which I'll need in order to describe the sections and the curves that we're going to see. First of all, let's think about the axis of the cone. Now, that's the line that runs from the point down through the centre of the base and out there. So that's the axis. The generator of the cone, well, that's any line that runs down the side of the cone like that. And the generator, think of it as being a pendulum, a piece of string tight to there. It swings round here and it maps out this curved surface of the cone. So, let's begin by looking at the cuts or sections that we can make. Well, one of the simplest sections that we can make is to cut across and perpendicular to the axis of the cone. And what do we get? We get that well-known curve, the circle. Okay, let's not now cut perpendicular, let's cut at an angle. So we're going to cut at an angle to the axis of the cone. We're going to keep the cut within the physical dimensions of the cone, and what do we get? We get a curved surface, a closed curve again. This time it's an ellipse, a kind of flattened circle if you like, but its name is an ellipse. Let's put that back on, and now let's take a cut which is parallel to the generator, parallel to the edge of the curved surface. So there's our edge of the curved surface, and this is the cut that we're going to take parallel to that edge. So we make the cut, and there we've got an open curve this time, not a closed one, it's an open curve, and it's called the parabola. Putting that back together, what I want you to imagine now is a double cone. Now, what do I mean by a double cone? I mean another cone sitting on top of this one, point to point. So imagine we've got this cone here, and we've got another cone up here. And again, I'm going to take a cut, which this time is going to be parallel to the axis of the cone, coming straight down there. And you can see the cut there. Now, once I make it, there I've made the cut, I'll actually be making the cut through the cone up here. And so there'll actually be two pieces to the curve. One from the upper cone and one from the lower cone. And that's a hyperbola. It's got two branches to it. So those are our three conic sections. Sorry, miscounted. Those are our four conic sections. The circle, the ellipse, the parabola, and the hyperbola with its two branches. Now, the conic sections were first discovered by Monachus in about 350 BC. Monachus was an ancient Greek. He, in fact, had three different cones, but he took the same cut in each cone in order to generate three of them. Here we're disregarding the circle because that's obviously the simplest cut to make. Later, Apollonius who was around about 200 BC, generated this idea of making the cuts all in exactly the same cone.